Wonderful. Okay, so let's quickly take a look at this one. All right, so when we're doing a problem like this, first things first, you always want to just, make sure that you double read the question so you know what's going on. This is an evaluate question. Whenever you are asked to evaluate a function, evaluate means what? Solve. Not really solve. When we say, now, let me tell you why. Okay, well, kind of. When we say the word solve, that means we're going to find the value, we're going to isolate a variable and find its value, right? That's really not what we're doing here. Evaluating is something different. Evaluating means, value means what in math? Okay, value means number. So when we evaluate, we're going to plug in an input value and calculate the output value. That's what we're doing. So we're plugging in a value of -6 for x, and we're just calculating what the output value for the function is. So y, right? Finding the y value. Okay, but when we do this, now normally this is very simple. We're just plugging in a number for x and seeing what we get for an answer, right? But with a piecewise function, it's slightly more complicated because we have to figure out which piece we're using. We're going to plug into only one equation, but which one? Depends on the domains, right? So -6, now that puts it where? Top or bottom?
Top.
Bottom, top. Puts it on the top because of this, right? Now the question came up every period, this question, now this is a great question. How is -6 less than -5 when 6 is bigger than 5? Okay, exactly. And the way to remember that, don't be embarrassed, that's a good question. Here's how you remember it. Right here, please listen. Okay, so here's how we remember that. Whenever you're trying to, and this is a really easy mistake to make. People make this mistake without, even though they probably know how to do it. It's easy to get careless and make this mistake, and even in calculus, people make this mistake all the time. So think about this. Less than always means left of on a number line. So if we're talking about the number -6 relative to the breaking point, -5, well, -6 is less than -5, so it's less than, right? Okay? So then we know we're in the top piece and not the bottom piece. We can just ignore the bottom piece. So all we're doing then is plugging -6 in for x in the top equation. That's it. Okay? So then f of -6, I'm just going to plug -6 in right there. Equals 2/3 times, I'll make it -6 over 1 to make it a fraction, -6. Well, what is, if I could reduce, but this is pretty easy. If I just multiply straight across, which is what I do with fractions, what do I get here? -12 over 3. And what is -12 over 3? Yeah. -4 minus 6 equals? -10. Yeah. So that's my answer. Okay, good? All right. So what I want to do today then, I want to, being as we're kind of getting into, newer stuff now, I want to really make sure that we're organized in here so we get the right stuff done before we go to the lab. So here's the sort of the plan for the day. I want to make sure that we're doing these things. We can check one off the list. I should have added watch some great skydiving too. We'll check that out too. Okay, so the first thing that we went through, and this is kind of a review of what we did yesterday, is knowing how to evaluate piecewise functions. Done. Okay, but the other two things on the agenda still, we got it. And these are big items. So I'll try to be real honest with you about, how big a deal is this? How complex is this? Sometimes it'll just be, we're in and out, it's easy stuff, we'll go practice. This is not that way. This is a little bit tougher. It's not like there's any one part of this that's so amazingly difficult, but it's a process. And processes involve many parts. And so we got to be able to put all those parts together. So we want to do two things. We want to be able to graph a piecewise function if I give you a piecewise function, and we want to be able to turn that around. And if I give you a graph of a piecewise function, write the piecewise function that goes with the graph. Okay? First things first though, let's start with graphing a piecewise function. So here's what we got going with that. Okay, so let's remind ourselves, and I want to absolutely insist, I want everybody the proper way to be learning this now, what I expect to see from you is literally, if you have to turn your desk, do that. But I want to see eyes up here, tracking me, watching this stuff. If you have anything to say, please raise your hand and I welcome it. But I want it to be productive. Okay? And then we'll get some practice with this. But this is a big deal. We got to get this conceptually in our brains, and that takes a little work. You got to really concentrate on this. Okay, so piecewise functions. Now here's an example that I think we just took a glance at yesterday, but we didn't really do much with. So let's get back into it and go further. Ignore that little line in the middle. Okay, that shouldn't be there. Really, you just get like rows in a piecewise function. Each row corresponds to a piece. If I were to organize this, in fact, I'm going to do this real quick. I just want to try to cross that guy out a little bit so we don't see him, because he really shouldn't be there. Okay? So each row, if you look at this, it's really important to see the structure of a piecewise function. Each piece of the piecewise function has two parts. There's going to be the equation part that tells you what the graph looks like. So that's just a line, isn't it? mx plus b, 1/2 x plus 3/2. And then next to that, there's going to be the domain part, which tells you where that piece of the function is switched on. Okay? So in the top function, we get the line y equals 1/2 x plus 3/2, which is switched on wherever x is less than, so to the left of, +1. Okay? The other piece of the function is a different line. It's the line y equals -x plus 3, which is switched on when x is greater than or equal to 1, so to the right of +1. Okay, I want phones. I'm going to collect phones today. If I see any phones out, I'm taking them and I debate whether to get them back. Okay. So this is what the graph of that piecewise function would look like, and let's just make sure we understand why. Now, where's the breaking point? In other words, what's the x value where we make a transition from one piece to the other? 1, right? When x is less than 1, we're on one piece. When x is greater than or equal to 1, we're on the other piece. So 1 is the breaking point. That's where we're making the jump, right? Okay, AJ, please. I'm sorry. Okay, so there's my breaking point. A vertical line at x equals 1, okay? And that's going to break this up into a left piece and a right piece. Now, based on our function up here, which is the left piece? And look at the domains. Okay, good. It's at the top one, because that's where x is less than 1. So wherever x is to the left of the breaking point 1 is where we're going to graph this guy, right?
Yeah.
So that's going to be the left piece. Okay, right there. And then the other piece is graphed where x is greater than or equal to 1. So that's the right piece. Okay? Make sense? Now, technically, we got to pay attention to the endpoints also. Being as we graphed the top one first, that red piece, does it get to keep the endpoint or not? The endpoint at x equals 1. Is that included? It can only be included in one piece. In this case, x equals 1 is included with the red left function or the blue right function. And how do you know? Okay, good. So the bottom one, here's the key, right? The bottom one includes an equal sign. And so that means at x is actually equal to 1, we're on the blue function. So the blue one keeps a solid endpoint there. The red one, technically, has an open circle because it's not including the endpoint. Okay? Right? Now, in this case, it's not a big issue because the two pieces actually join up. It doesn't always happen that way. But this time it did. So in this case, as the ant walks along from left to right, he doesn't have to jump at all. He just stepped from the red right onto the blue. Okay? Let's look at one of these. Let's do one of these now. Okay, so what about this guy? Right? Let's do this one together. How many pieces in this piecewise function? 2, left and a right. Where is our breaking point?
2.
At 2. Okay, so let's put in a breaking point line. I missed it a little bit, I'll scoot it over. So there's our breaking point, right? X equals 2, that's going to divide it into a left and a right piece. Now, which of these two is going to go on the left? Okay, which one? Bottom one. Okay, bottom was on the left because X is less than or equal to 2, right? So then here's what I'm going to encourage you to do. When you're graphing these on graph paper, which I'm going to want you to do, literally write the equation of the left piece on the left side. So to the left of the breaking point, we'll just write y equals negative x plus 1. Okay, on the other side, on the right side, I don't have much room here, but I'll just kind of put it up here instead. We're going to write the right equation. Okay, and then we're gonna graph those two lines, plot those two lines in their regions. Okay, now normally it would be very simple if I just told you guys, if I just gave you the problem, just graph the red line, y equals 2/3 x plus 2/3. You all could do that. If I said just graph the blue line by itself, no big deal, y equals negative x plus 1. You can also do that. The strategy is always the same when we graph lines. We're going to plot 2 points and connect and extend. The only difference between me having you do either one of those easier problems or maybe the little bit harder problem of a piecewise function that joins them is that you're not graphing the entire line. You're only graphing the line where it's switched on. So I'm only going to graph the red graph to the right of the breaking point, right? My pen is only going to be on the paper to the right of the breaking point, and then I'm picking my pen up because the red line does not extend past the breaking point to the left, right? The blue line, instead of graphing it everywhere, I'm only going to graph it with my pen down to the left of the breaking point, but not to the right. That's the only difference, okay? So that adds maybe just a slight wrinkle. When I want to graph these things, I generally want to pick 2 points that are convenient, meaning they're on the correct side of the breaking point. The blue one's a piece of cake because it includes the y-axis. So let's do that one first to warm up. Right. If I want to graph the blue line, y equals negative x plus 1, what's the anchor point, we could say? What's the first point that I'm going to plot? What's one really obvious point that this line goes through? Y-intercept of 1, right? So if I do a y-intercept of 1, it's right there, isn't it? Okay. What's my slope of the first line? Negative 1. Okay, now we can always use slope to get a second point. If the slope of this line is equal to negative 1, anytime I get an integer slope, don't I just have a 1 on the bottom? Okay, so that's just telling me that I'm going to go rise by negative 1 and run by positive 1 to get my second point right there, right? I got 2 points, connect and extend. That's it. So all I have to do then is just connect those points and extend, but notice that I stop. I pick my pen up when I get to the boundary line or to the breaking point, right? Because it's only turned on to the left of that. Now, am I going to attach a solid or an open endpoint to that left blue piece? Solid, good, because of that, right? So we're going to do that. Done. I got the blue. I'm halfway done. I got the blue piece taken care of. Now we got to do the red piece. The red piece is a little trickier. It's a little trickier because, for one thing, the x-axis or the y-axis is clear over to the left of our breaking point, and so we're not using the y-intercept as a point. That's okay. We don't really need to. What you can do in those cases is just make a little t-table. So I'm going to put my t-table. Normally I'd put it on this side, but there's not enough room. So I'm going to put my red t-table over here. Let's find a convenient value for x. And it pays to give this a little thought and not jump into it. See if we can find one that's going to work well. If my equation is y equals 2/3 x plus 2/3, that's kind of tricky. Wouldn't it be nice if I could pick a value of x that's going to give me back a non-fraction answer for y? Right? What might work? 6 would work. Yeah, 6 would work. Actually, Would 6 work? Yeah, it would. 6 would. What's another one that would work? 3 is actually not going to work. I'll tell you why. Because if I put 3 in, I'm going to get 2 plus 2/3. This is kind of a tricky one. No matter what I'm getting for this answer, I'm going to be adding 2/3 to it. Well, you know, why not? Let's just try 2, because 2 is the breaking point anyway, right? So if I plug 2 in, what happens? So if I plug 2 in for x, I get 2/3 times 2, which is what? What's 2 times 2/3? 6. Multiply straight across. Yeah, we don't want to do mixed numbers, though. If I just multiply straight across, what do I get? 4/3, okay, plus 2/3. 4/3 plus 2/3 is how many thirds? 6/3, which reduces to 2, right? So everybody see that. Now don't lose your train of thought. If I plug in 2 for x, we got back 6/3, which is 2 for y. That just corresponds to the point with coordinates 2, 2. Good luck. Take it to him.
Good luck. Hope you lose.
Sad part is he will lose.
Yeah, he will.
Okay, so we get the point 2, 2. There's a point, right? Now I can use a slope triangle to get a second point. I don't have good color. I'll use orange. Okay, so for my slope triangle, what's the slope of the red line? 2/3. So I'm going to go up 2, positive 2, and over 3. And so I create a second point kind of right over there. And now I can just connect and extend forever in that direction. Open or closed endpoint? Open, because it doesn't include the equal sign. Remember, only one of the two can ever be closed. So the blue one's closed, the red one's got to be open. That's it. Okay, that's my graph. Right? So that looks pretty messy. To summarize that, this is kind of what we got, isn't it? We got a breaking point at x equals 2. On the right side, we got an open end point at 2, 2. And then it extended up 2 and over 3 and on. On the other side, it was pretty simple. We had a y-intercept at 1, slope of -1, closed endpoint on the boundary. Right? Okay, no big deal. Okay, what about this one? Does that look harder or easier?
Easier.
Looks harder, but maybe. It actually, I think AJ's right. I think this is actually a lot easier than the other one. The other one required us to actually find 2 points and use slopes, and I mean it was a little tougher because we had slopes involved that were not 0. Look at this one now. How many pieces are there in this function? 4. So I should get 4 separate parts to the graph, right?
So do we need 4 different breaking points then?
That's right. So we're gonna have lots of breaking points. So to keep this organized, how about if we color code this so we got red piece, blue piece, etc. Now let's focus on the red piece. Only look at the red line first, the red row. That's one piece of this function. Remember, there's 2 parts to each row, to each piece. The comma is what separates those. The equation is always on the left, and then the domain, which tells you where it's switched on, is on the right. Well, the equation's pretty simple for that first one. What is it? Y equals 1. Now, what's that look like? What's y equals 1 look like? Okay, so but if it's going to be a line, okay, it's going to be a horizontal line, good, with a y-intercept at 1. That's it. If you ever get y equals a number, then what that means is every y value on that whole line is equal to that number, so they all have a y-coordinate of 1, including the y-intercept. So if I were to graph that, it just looks like that line that goes forever, right? Except that we're not graphing the whole thing. We're only going to graph the piece where it's switched on. It's switched on here, where x is greater than or equal to 0. Okay, so that means that x is 0 right there, right? So when x is greater than or equal to 0, so this way, I'm going to start graphing the line. But x also has to be less than 1. I gotta put an open circle there, and it's where that interval in the middle is trapped. Does that make sense? It's an and statement. X is greater than or equal to 0 and less than 1. So it's trapped between those two endpoints. So doesn't it end up looking just like this? Does that make sense? Okay. What about the blue piece? What's the equation for the blue piece? Y equals 2. And so if I were to graph that line, the line goes forever, y-intercept of 2, but I don't want the whole thing. I only want the part where it's active, where it's switched on, and that's right there. So I'm going to have, it looks like I'm going to have a closed endpoint at x equals 1. So if I start at 1 and I go up, I'm going to have a closed endpoint there. It's got to be greater than that, so it's going to be to the right of that endpoint, right? Because it says x is greater than or equal to positive 1. To the right of positive 1, to the left of 2, right? So I'm going to put an open endpoint there and connect them. Agree? That's all I want, though. I don't want the whole thing, just that little piece. Right? How about the next one? See if we can just kind of think this one through. What's the graph going to be? Y equals, so what's that look like? Okay, horizontal line, y-intercept of 3, but it's only switched on, yeah, where x is going to be to the right of 2 and the left of 3, and I get to close the endpoint at 2. Right? And then finally, I get y equals 4, horizontal line, y-intercept 4, closed circle at 3, closed endpoint at 3, open endpoint at 4. Yep. Right? Okay, so you guys try, please. Well, actually, you know what? We'll do this together. Let's try. I've got a piece of graph paper so you can really see this thing better. Let's try that. What about that guy? This is the kind of thing you're going to be doing. So we're given a piecewise function. We got to come up with a graph. So first of all, where's the breaking point? 4. Everybody agree? Okay. So how's that? Right there? Everybody agree? Okay. Take a second at your table. I want to establish real quick, which is the left and which is the right piece. Okay, make sure you agree on it. Take just a second. See if you agree. I know it's a lot. Yeah, no, we can't wait. We're going to get a full lap day tomorrow, though. How's that? Good. 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 Because this is hard. Oh, that's fine. That's fine. So we'll be in the lab anyway. Okay, so what do we get right here, please? What do we get? Which one's the left function? Top one's left. Okay, good. So let's do that one in red then. We know the top one is going to be left. This is kind of a way I like to show just a brief summary of what's going to be happening there. That's the left function, right? So we know that the arrow is going to go to the left, right? So it's going to go that way. And we know that it's at left to right a positive slope. So we even know that, don't I? It's going to slant uphill from left to right. What kind of endpoint do I get? Okay, so it's going to be open because it doesn't include the endpoint, right? The other one, we'll make that one purple. Okay, the other one is going to be to the right. It looks like it's also going to be sloping up. It's a positive slope, right? Does it include the endpoint? Okay, so that's close, right? So we know that's basically the look we're going to get. Now let's put those in there. So let's do the red one first. On the red side, we've got the line y equals 1/2 x plus 1. That's a really easy one to do, isn't it? Where's the obvious point that we start with? Yeah. Y equals 1. Y-intercept is 1. What's my slope triangle telling me to do? Okay, up 1 over 2. So there's my second point.
Okay.
Connect and extend. And we said open endpoint, right?
Yes.
Left piece, done. Okay, right piece. Over on the right side, we've got the line, we'll write the equation down, y equals 1/4 x minus 2. This is a little tougher. We need a t-table here because we don't have the y-axis to get that first point for free. So if we make our t-table, what's a nice convenient value for x? What could I multiply 1/4 by and get back a non-fraction? 4 would work, wouldn't it? 4 times 1/4 is 1. Subtract 2 from that? -1. So x equals 4, y equals -1. Over 4, down 1. There's a point. Slope triangle to get the second point. That's easy. So what do I do? Up 1, over 4. So there's another point right there. So we'll just connect and extend. We said it was a closed end point. Done. How about that? Okay, so then the last piece of this, and we're done. You guys, this is great. You guys, this is the fastest thing in Algebra 2 classes ever. It seems like you guys are getting this. Do you feel like you're getting this?
Yes.
Okay, wow, this is amazing. This is great. Fantastic. Okay, let's try the last piece then. The last piece is, what if I give you a graph and I want you to fill in the piecewise function? Okay. So now I'm going to do this all year long. This is a really important part of Algebra 2. To be able to know Algebra 2 well, to learn it well, you got to be able to turn the process around. If I give you a graph, you write the function. What I'm always going to tell you to do all year, and this is a really valuable approach to doing this, it works great, is build a template. I'm always going to tell you to build a template, meaning fill in what you know the answer is going to look like, and then go back and fill in the individual pieces. But I know that this is going to look like a piecewise function with how many pieces? 4, right? So I know right away that my template's going to look like this. I'm going to get f of x equals, and then I'm going to have 4 pieces, right? 4 different equations. Each of those equations is going to get its own domain. That's what my template looks like, right? Let's fill this thing in then. Oh, yeah, it's pretty messy. I'll get rid of that. But you get the idea.
Okay.
Oh, hang on. Maybe you don't. Okay, I'll tell you what. Let's do.
Anything else already done?
I guess I skipped one slide there. Let's do this one instead. He's going to have much time.
Already had that one written down.
Sorry.
Sorry.
Okay, we'll do this one. How many pieces in this template? This will be a little quicker. 2 pieces. Okay.
All right.
So we get f of x equals, and then we're going to get a top piece and a bottom piece. Let's do the left one on the top. How about? So where's my breaking point this time? Okay. So there's my breaking point at x equals -4. Now the left piece is where x is less than. Are we going to include an equals to? Yeah, we do, because we got a solid endpoint, right? So we know over here we're going to get x is less than or equal to -4. That's the left side. So let's come up with the equation of this line. Now, we know how to do this, right? If we want to come up with the equation of a line, all we want to do is we want to figure out what m and b are, because our answer is going to be mx plus b. We just got to specify, though, what's our m and what's our b. Well, first of all, we can just, by inspection, by just looking at the graph and making a slope triangle, what's the slope of the left piece? 2 over 1. Good. So if it's 2 over 1, that just means 2, doesn't it? Right? So we're going to put a 2 in for m. To find b, I have to be able to plug in a solution, values of x and y that are on the line. So let's find a convenient point. How about either one of those would work, but I'm going to suggest that maybe that's a good one because it's on the x-axis. It's got a 0 coordinate. Yes, ma'am. Yes, ma'am. Passes are there. So what are the coordinates of that piece? Okay, hang on. Be real careful. 0, -5, or -5, 0. Remember, x first and then y. So we're going to go left -5 and up 0, right? Does that make sense? So then 0 is going in for y, -5 is going in for x, And that's gonna allow us to solve for b. Right? If I plug that stuff in, don't I just get 0 equals 2 times negative 5 is what? So what's b? Okay, if I know b is 10, and I know that m is 2, negative 2, what's the equation?
2x plus 10.
2x plus 10, mx plus b, right? So we can fill in that blank. This one is 2x plus 10, right? Okay, now the right one is easy. Right one's a piece of cake. What's the domain of this one? Well, it's everything to the right of, but not including, negative 4. So how do I say that? X is greater than negative 4. And this is a really simple one because we can see b. What's b? Want me to scoot it up? Can everybody see that? What's b? Negative 9. And if I use a slope triangle here, what's m?
Negative 1.
M is negative 1 over 1, which is negative 1. So then m is negative 1, b is negative 9. What's my equation?
Negative x minus 9.
Yeah, negative 1x. We wouldn't write the negative 1. We just write the negative, right? Negative x minus 9. You got it.
Some more cool videos.
Are we getting down to the wire here? Yeah. Okay, let me finish taking roll. I'll let that's. Is that you guys? Is that you say uncle? Is that enough for one day? Okay.